Hi, and welcome to the fifth lecture of this deep learning course. Today we're going to talk about regularization. We've already briefly touched upon this topic in the first lecture, but only in the context of very simple linear regression problems. Today we're going to cover the topic of regularization more broadly and with a specific focus on deep neural networks. Why is regularization important for deep neural networks? Well, it's particularly important for deep neural networks, actually, because typically deep neural networks have a large number of parameters. Sometimes the number of parameters is even larger than the number of training samples. And that's why regularization is a very important topic in this context. This lecture is structured into 5 units. In the first unit, we're going to talk about parameter penalties. In the second unit, we're going to cover early stopping, and then we're going to talk about ensemble methods and one particular ensemble method that's popular in the context of deep learning, which is called dropout. And finally, we're going to talk about data augmentation, which also can be viewed as a particular form of regularization. But before we start, let's briefly recap from the first lecture where we talked about model capacity, model overfitting, and underfitting. These are 3 plots from the first lecture where we have fitted a polynomial of various degrees to a data set here in green. Green dots are the training points. On the left, we see a polynomial of degree 1. On the middle, we see the fit of the polynomial of degree 3. And on the right, a polynomial fit with degree 9. And we can see that if the model capacity is too low, in other words, if the model is not flexible enough, if it has too few parameters, both the training error and the test error are high. We never fit the test setters nor the training points well in this case, and this is called underfitting. On the other side, if the model capacity is too high, if we have too many parameters, in this case we have 10 parameters for a polynomial of degree 9, then we can fit the training set very well. In this case, we minimize the training error to 0 even. Like this red curve goes precisely through all the green training points. However, the test error or generalization error is very large. The model doesn't generalize well. For instance, this point here is very poorly approximated through this red curve. And this is called overfitting. Now, when we talk about regularization in the context of deep neural networks, what we want to do is we want to take a model from the third regime, a model that's too flexible, and bring it to this second regime where the capacity is about right. And why do we want to go from the third to the second regime? Well, the reason is that for many real-world problems, it's very hard to specify by hand the right representation, the right number of parameters, the right representation that has a small number of parameters. It's much easier to specify a larger model class, or a model that is able to represent a larger class of functions, such as a neural network with many layers, and then to restrict this class of functions again using soft constraints such that generalization is obtained. That's why we're going from the third to the second regime, because it's easier to specify a more generic model and then apply these regularizers as a soft constraint, as we'll see today. Yeah, so here's 2 more plots from the first lecture. On the left, we see the training and generalization errors for this polynomial fit of various degrees. We see that the terms of generalization error is attained here in the middle. So what we effectively do if we go from this over-parameterized, from this overfitting regime here on the right to the point where we achieve good generalization is that we're effectively reducing, we're effectively paying a price. We're increasing the bias for reducing the variance. Remember again that in this overfitting regime, the estimator, the parameter estimator, has a large variance but a low bias. In practice, we want, of course, both to be small. We want to have small variance and small bias. But our hope is that if we are willing to pay a slightly higher price, a slightly higher bias, and we can significantly reduce the variance, and this leads to better generalization. So the goal is always to minimize the generalization error, despite using this large model family, this deep neural networks that specify very flexibly a large function class. I think this is another diagram that illustrates this at a very high level, a very intuitive level, quite well. So what this should illustrate here is that both the data as well as the regularizer are constraints on the space of functions. And so they both constrain the possible outcome of our estimator, the possible solution space. So in red here, we have the function space. Let's say we are considering a feed-forward neural network with 3 layers, a certain number of hidden units per layer. And in this red area, these are all the mappings that this neural network can represent, all the functions for any possible combination of parameters W. This is, of course, an infinitely large set. Right? It's just a 2D illustration here. Now, the regularizer constrains this space by putting a soft constraint on this function space, such that functions that are close to some particular location in that function space are more likely. Similarly, the data, the training data, is also constrained because we are minimizing some negative log likelihood error. We're maximizing the likelihood of the data. And so this can also be viewed as a constraint on the function space. And the solution that we're seeking really lies here somewhere at the intersection of the function space and the regularizer and the data. The data is not necessarily, the training or the data distribution is not necessarily overlapping with the function space, because even for we're using very large deep networks, nature is still complex enough to be more complicated than all the functions that we can represent. So we're always making an approximation, but we're trying to make an approximation that is good in terms of fits the data well, but at the same time is not too complicated, which is encouraged by the regularizer. Good, so let's start now with parameter penalties. Let's use the common notation that we've used before, calligraphic X, for denoting a data set, XY. So this is again, in all the rows of X are the inputs, all the rows of Y are the outputs. Here we have one-dimensional outputs in this example, but could be more. And let W denote the model parameters. So this is a generic notion of model parameters. In a multi-layer perceptron, this would be a big vector that concatenates all the flattened weight matrices A, we called them before. And so we take all the weight matrices A of all these layers, we flatten each of them, and we stack them together into a big vector. This is what we generically call W here. We can then limit the effective model capacity by adding a parameter norm penalty, R to the loss L. So the total loss of the dataset X and the parameters W equals the original unregularized loss on the dataset X and the parameters W, plus a regularizer on the parameters W, where alpha is a hyperparameter that controls the strength of this regularizer and can be chosen using cross-validation, for instance. Now you can already see from this equation why this is called a parameter non-penalty. It's because we're penalizing here, not like this term does not depend on the data set. It just depends on the parameter, and it's effectively implemented. You can't see it from this slide here yet, but you will see on the next slide that it's effectively implemented as a simple norm on the parameters W. Right. So R, this regularizer, should quantify the size of the parameters or the model capacity. We want to have few parameters that are active. We want to have a small model capacity that still fits the data well. And minimizing L tilde, this total loss, will decrease both L and R. So we have this competition between L and R here. Right? We want to have a model that fits the data well, but at the same time is not too complex. And this is encouraged by optimizing both of these terms simultaneously, by having them both as a single objective combined with a addition here. Typically, R is only applied to the weights and not to the bias of the affine layers. Remember again, the only parameters of a simple multi-layer perceptron are in the affine layers, and they are the weights, called it the matrix A, and the bias vector B. And the reason why we typically only apply R to the weights is that we want the bias to be flexible. Applying a regularizer that encourages the bias to be close to 0 is typically not a good idea, because the bias wants to be not close to 0. And the second argument is that there's much more weights than there is biases, right? We have much fewer biases. So it's not so important to constrain the bias, and we don't know as much about the bias as about the weights. But what we want to do is we want to drive the weights closer to the origin. We want to make the weight vector W closer to 0. And why do we want to make it closer to 0? Well, in the absence of any prior knowledge about the problem, this is the best we can do. If we have prior knowledge, we can, of course, incorporate this into our regularizer. But if we don't have prior knowledge, then this is the best we can do, because if we have small weights, we have seen this already in the first lecture, for the case of linear regression, if we have small weights, this leads to less complicated solutions, also for deeper neural networks. So it's a very simple regularizer to encourage simplicity of the model. Here's a small intuition about this. It's a very hand-wavy and high-level example, but maybe it can help a little bit with this intuition. So suppose there's two very simple networks that make predictions on inputs X and Y, so the two-dimensional input. And let's suppose these two networks are fed with nearly identical X1 and X2 that are nearly identical and close to M1, for instance. Then here on the left, we're going to predict 2, and on the right, we're also going to predict 2. So the output is roughly the same. However, the second network has much higher weights. So it is much more brittle in a sense. If the test distribution is slightly different from the train distribution, this means that the prediction will be worse. Right? So it's representing the same thing, but with a more complex function. And here's another illustration, and we're going to look at some of these plots in the following slides as well. This is a geometric view on the problem where we're looking at the parameter space now. Here we have a two-dimensional parameter space. Of course, we have much more parameters typically in practice, but for the sake of simplicity, we draw two parameters, W1 and W2. And we have the contour plots of the objective function in green and the regularizer in red. Now, what is a contour plot? A contour plot is a plot of curves where every point on the same curve corresponds to a location where the function takes the same value. And so for instance, here on this ellipsoid here, we have the same functions of the objective. And then the value increases with increasing ellipsoids here. So you can think of this a little bit as the height lines on a hiking map. So in this case here, for instance, you can think about this as a quadratic in 2 dimensions, or a parabola in 2 dimensions, where we have a minimum here, and then the slope is upwards. It's increasing more in this direction because the height lines are closer together. It's increasing less slowly in this direction here. So this is the objective function. This is the minimum here, and because in this simple case it's convex, if we would apply gradient-based optimization to it, we would end up at this point, at the minimum. Now what we do when we apply parameter penalties, we add a regularizer. In this case here, in the simple illustration, we have an L2 regularizer where this contour plot looks like this. So we have concentric circles as these contour lines, where we pay an increasingly high price if we go further and further away from 0, 0, which is where this regularizer is 0. And now because we have these two competing objectives, if we optimize the joint objective, the summation of the objective function with the regularizer, so this expression here, then the optimum is no longer here, but it's somewhere here, because these two objectives are competing with each other. You can see that now in this case, the value of W2 has been significantly reduced by this regularizer, while the value of W1 has increased a little bit. But overall, this regularizer ensures that the loss function added, that the norm, the L2 norm of this parameter vector is small. And so we have these two competing objectives here, where the optimum is then somewhere in the middle. Okay, so now let's look at L2 regularization, which I already mentioned, in a little bit more detail, more formally. L2 regularization is one of the most common forms of regularization in deep learning and also in machine learning in general. In deep learning, it's often also called weight decay. If you heard the term weight decay, and it typically refers to L2 penalties, L2 parameter penalties. And we have also used the term ridge regression for L2 regularization in the context of linear regression. So this weight decay or L2 regularization is simply a L2 penalty. So R of W is a squared expression of the L2 is a squared L2 loss here on the parameters W. So each element of this vector here squared and added up. So we can then write this total objective, which comprises the unregularized loss and the regularizer as such. Here, this is just a different form of writing the squared L2 norm. It's an inner product of W with itself. Now, let's try to get some intuition about this. What does this do to our gradient descent optimization? The parameter updates during a gradient descent algorithm, such as stochastic gradient descent, are given by this equation here. So the parameters at the next iteration are the parameters at the current iteration minus some step size, eta, we've called it, times the gradient of the objective function with respect to the parameters W. So here's the combined objective function, L tilde. Now we can plug in this expression here, and the gradient of this is the gradient of the original objective function here, which we haven't further specified at this point, plus the gradient of the regularizer, which is simply alpha W. at the previous iteration. Okay, now we can slightly rewrite this by pulling this alpha eta out. So we get 1 minus eta alpha. This is this eta alpha here, wt, minus eta and the gradient of the unregularized objective. And what we can see now is that this is very intuitive. What the weight decay is doing is very intuitive, because what we're effectively doing here is we are decaying the weights of the previous iteration before the gradient update. And we're doing this at every iteration of the optimization algorithm. We're taking the previous weights. Eta and alpha are small, so this is this expression here, they're small and positive. So this expression here is a number that's slightly below 1. So we're taking this parameters at the previous time or iteration, and we're making these parameters slightly smaller, slightly closer to the origin, closer to 0. And then we're doing our gradient update. So we're effectively decaying. We're making these weights smaller during every iteration of the gradient update step. Now this was for a single gradient update step, but what happens over the entire course of training? Can we also make a statement about the overall training? In order to do this, let's make a simplification. Let's consider W star as the optimal value, the optimum of the unregularized objective or loss function. So W star is the solution to the unregularized objective. If I show this plot again, this will be here. And let's consider a quadratic approximation, L hat. Don't be confused with L tilde. So now we're having L hat. This is just indicating, the hat is indicating that this is an approximation of the unregularized loss around W star, around the optimum. So what does this look like? Well, if we have a quadratic approximation, this is basically just a multivariate Taylor series expansion, which I've written down here. So here's the quadratic approximation is equal to the loss function at W star, the optimum, plus a linear component, the gradient vector times W minus W star, plus the quadratic contribution here in this Taylor series expansion, which is W minus W star transpose H, which is the Hessian matrix, so matrix with the entries being the second order derivative of the objective. We have the gradient vector here and the Hessian matrix here. So this is the second contribution, so the second order derivative. And so we have a quadratic term here. So it's W minus W star, H, W minus W star. So we have a linear and a quadratic term with respect to W. Now, because we have assumed that W star is the solution to the unregularized objective, we know that the gradient of the unregularized objective is 0, because it's the optimum, it's at the minimum. So this term here vanishes. So we're left with this term and this term. This is this expression here. So when now adding this is the quadratic approximation to the unregularized loss. When adding to this expression here, the regularization term, this approximation becomes this term here. So in this case here, I've highlighted the new term here. This is the regularization term, which we don't need to approximate. It's already quadratic. It's already simple. We don't need to do anything about it. So we have now this quadratic approximation on the left of the unregularized loss plus the regularizer. And we just also call this L hat. Okay. So this is just copied from the previous slide. Okay, this is the same equation as the equation on the previous slide. Now, what we know is that the minimum, let's call this minimum of the regularized objective, not W star, to not confuse ourselves, but let's call it W tilde. Let the minimum W tilde of the regularized objective, of the regularized approximated objective, L hat, this minimum is attained where the gradient is 0. Right? And because it's a quadratic objective now, we can find that location. Okay, so what is the gradient of this expression with respect to W? Well, the first expression here does not depend on W. It just depends on W star, which is constant. So this goes away. This expression here, derived with respect to W, is HW. Now we have using W tilde as the solution already. So this is now replaced by W tilde. So it's HW tilde minus W star. This is just linear algebra. It's the gradient of this expression. Plus alpha W tilde. Now here we have also again like the derivative of the quadratic term here is a linear term. It's a alpha W tilde. This is the second expression here. So we get this. Now we can take this HW star and put it on the other side. Right? And then we are left with H plus alpha I. So we've put this alpha into these brackets here. H plus alpha I. I here is the identity matrix. Nothing has changed. It's just like writing it together into one bracket times W tilde, because both H and alpha are multiplied with W tilde. And now we can take this matrix here on the other side by inverting it. So W tilde, the solution is H plus alpha identity matrix inverted times H times W star. And therefore we see that as alpha approaches 0, as this term here, the regularization here, approaches 0, which means effectively we're not regularizing anymore, we're removing this term. The solution W tilde approaches W star because we have H inverse times H, which is the identity. So we have W tilde approaches W star. And this is intuitive, right? If we remove the regularizer successively, if we're making this alpha smaller and smaller, then of course the regularized solution comes closer to the solution of the unregularized objective. So this point doesn't lie here anymore, but it's closer to the solution of the unregularized objective function if we make this regularizer smaller, or the influence of this regularizer smaller. Okay, so this is what happens if alpha approaches 0. Now, what happens if alpha grows instead? Right? If it grows to large values. In order to get a better understanding of this, we're gonna apply the eigenvalue decomposition on the Hessian matrix H. The Hessian matrix is a symmetric matrix of real values because due to Schwarz's theorem, we can swap the partial derivatives of each element in that matrix, which means that the matrix becomes symmetric. And it's a matrix of real values, which means that the eigendecomposition has a particularly simple form. It's just a product of the orthonormal basis of eigenvectors Q with a diagonal matrix where at each element of the diagonal we have the eigenvalues, and then we have Q transposed. Right? Q transposed is the same as Q inverse because this is an orthonormal basis in the case of a symmetric matrix with real values. And we also know that the eigenvalues and the eigenvectors are real in this case. So it's all very simple. Now we can take this eigen decomposition of this matrix H and plug it into this expression here. What happens if we do that? Well, so this is the expression from the previous slide. We plug in, for H, we plug in Q lambda Q transpose on both places here. Then what we can do here on the right is, because we have the identity matrix here, so we can of course also multiply Q identity Q transpose, because Q and Q transpose cancel. So this is equal to this expression here. So we have Q and then multiplied with lambda plus alpha I, Q transpose. Yeah, and then we can apply this inverse operator on these three matrices. Right? And we do the algebra, then Q and Q transpose swap, and they become inversed, but the inverse of Q is just Q transpose. So we're left with Q, and then the inverse now of lambda plus alpha I times lambda, because Q and Q transpose have cancelled, right? They are the identity, times Q transpose W star. So this is the expression that we end up with. And if we closely inspect this expression, we see that the component of W star that is aligned with the ith eigenvector of the Hessian H is effectively rescaled by a factor of lambda I over lambda I plus alpha. Why is that? Well, Q transpose and Q, they are autonormal bases, which means they are simply rotation matrices. So we are effectively rotating W star onto the ith eigenvector. And then we're applying, so this is all diagonal matrices, right? So what we have here is effectively lambda I for the ith eigenvector of lambda I divided by lambda I plus alpha here. So this is the elements. These are the elements on the diagonal of this matrix here, lambda plus alpha I inverse lambda. So we are now rescaling by this factor, and then we are rotating the vector back with Q again. Okay. If you have difficulties understanding this general concept here, I highly recommend that you go back a step and have a look at the Goodfellow book. I think it's in chapter 2 or so, where the eigendecomposition is described very well. Okay, so the component of W star that is aligned with the ith eigenvector of H is therefore rescaled by this factor. Right. And what we can also see is that the regularization affects directions with small eigenvalues, but not with large eigenvalues. So if the eigenvalues lambda I are much smaller than alpha, then this term here, let's say alpha is 1 and lambda is 0.1, then this term here becomes very small. So the rescaling takes effect. But if we have eigenvalues that are very large in directions of eigenvectors, where the eigenvalues are very large, then this rescaling does not happen as much. Let's say lambda is significantly larger than alpha, then this alpha doesn't play a role here. So we are effectively getting back a scaling factor that's close to 1. So the rescaling is not really taking place. What does this mean visually? Okay, let's look at a diagram as the one that we've seen before. We see here the contours of the unregularized objective in green again, and the L2 regularized in red. And we have this point W tilde, where the competing objectives of the regularization and the unregularized objective reach an equilibrium. This is the solution to the regularized loss. And what we can see is that along the W1, along this direction here, the eigenvalue of H is small because we have a low curvature here in this direction. So this function slopes more slowly in this direction, right? which means that the eigenvalues of h in this direction are small. And therefore, in this direction, the regularizer has a very strong effect. It pulls this value here, this optimal value of the unregularized objective, far away, closer to 0 in this direction. However, in this other direction, where the eigenvalue of h is large, and where we have a high curvature, we are paying a much higher price when we move into this direction with respect to this original objective in green. So the effect of the L2 regularizer, which has this isotropic behavior where we have these concentric circles, is much smaller. We can see that in this direction here, W star changes much less compared to this direction. So a smaller effect of the regularizer. We can also look at a different type of regularizer, for instance, the L1 regularizer. Here we see in red the contours of the L1 regularizer, which look different from the L2 regularizer. And the L1 regularizer is simply adding a penalty, a parameter norm penalty, where the norm is actually the L1 norm. So basically every element of this vector W, taking the absolute value of each element and then summing them up. And the L1 regularizer results in a solution which is more sparse compared to L2 regularizer. And we can already see this from this plot here. You can see that compared to the L2 regularizer, now in this case, the W1 parameter is becoming even smaller. So it's trying to squeeze this parameter W1 to close to 0, right? So it's becoming smaller, while the other parameter is more flexible and free. So this parameter doesn't change much. It becomes even a little bit bigger, but it tries, the L1 regularizer tries to make one of these parameters closer to 0. So let's look at this phenomenon at using a very simple, concrete example with numbers. So here we have an example where we assume 3 input features x, and these features are 1, 2, and 1. And then we consider 2 different linear classifiers. So these are simple logistic regression models in this case, for simplicity. And these linear classifiers have the weights 0, 0.75, 0, and 0 to 5, 0, 5, and 0 to 5. And if we multiply W1 and W2 with x, we see that they have the same effect. They yield exactly the same result. Right? So 0 times 1 is 0, 0.75 times 2 is 1.5, and 0, so we get 1.5. And similarly, we get 1.5 when we multiply this vector with x. So the result is the same. But now, the L1 and the L2 regularizer prefer each of these solutions very differently. So let's look at the L2 regularizer first. So the L2 regularizer of W1 is, well, taking each element, computing the square, and then summing them up. So it's basically 0.75 squared, which is 0.56. And in the second case, we have 0.25 squared, 0.5 squared, and 0.25 squared, which is 0.375. And we can see that in this regularizer prefers the model 2 over model 1, which both have the same prediction. So in this case, optimizing the joint objective would lead to parameter vectors that are closer to W2 rather than W1. In contrast, the L1 regularizer yields for W1 a value of 0.75 and for W2 a value of 1. So the L1 regularizer prefers these sparse solutions where a lot of the values are close to 0 over a solution with more homogeneous values. That's the difference between the L1 and the L2 regularizer. And here is a very simple graphical example that I took from the Introduction to Deep Learning course from Munich. So if we want to classify this picture here as a dog, the classifier might take different features such as it's furry, it has 2 eyes, has a tail, has paws, has 2 ears. And you can think of these features as some representations inside your deep neural network. Maybe in the penultimate layer of your deep neural network, it comes up with representations that model these different attributes. Now the L2 regularizer will take all information into account to make decisions. And the L1 regularizer will focus all the attention to a few key features. So it tries to classify this image by focusing on little features. Right? And depending on the application at hand, it's preferable to have either L2 or L1 regularization. And finally, I also want to show you the connection of parameter penalties to Bayesian map inference, because this L2 regularization has an interpretation as maximum a posteriori inference. For instance, when we consider L2 regularization, this can be interpreted as map estimation of the network parameters W with a Gaussian prior applied to W. Why is that? Well, here is the maximum a posteriori objective. So we are trying to maximize now the distribution over the parameters given the data. Now we can apply Bayes' rule here. So we have the likelihood. This is, if we would only maximize this term, we would have the maximum likelihood solution times the prior. Right? So this is equivalent. And then we can, of course, take the logarithm. So we get the log likelihood and the log prior. And then if we plug in for the log prior the Gaussian distribution with 0 mean and a covariance matrix, which is the identity matrix multiplied with alpha, this regularization strength, inverse, and we apply the logarithm to it, we see that this ends up in the regularizer that we've seen on the previous slide, alpha over 2 W transpose W. So here again we have converted the maximization problem into a minimization problem by taking the negative of this expression. Right. So we see that L2 regularization can be interpreted as Bayesian maximum a posteriori estimation of the network parameters with a Gaussian prior applied to W. And similarly, L1 regularization, as you can imagine, can be interpreted as map inference of W with a Laplace prior. Finally, I want to also briefly show how this could be integrated into a computation graph that you want to implement in terms of source code on, for instance, the educational framework. Well, because loss functions are just compute nodes, the combination of loss functions is really straightforward. It's a straightforward combination of compute nodes. So in this case, we have the unregularized objective or loss function L, and we have the regularizer that depends on both these parameters, W1 and W2. And then we have the total loss function, which is simply the weighted combination of these two, where I have used this orange symbol here for indicating the hyperparameter alpha.